Hi friends of the sun, welcome to the weekly reading group happening every Monday. It's today together with Carlos, and we're talking about adjoint flow matching. And if you want to join the reading group sessions yourself, all the information for that is down in the description. We have a Slack and stuff like that. It's just a Zoom call that anybody can join, so feel free to do that. Now, let's start the stuff, and then maybe you can quickly introduce yourself. I also want to know, like, where you were at NYU. Who was your professor?
Yes.
When did you then go to Meta?
Yeah.
Why did you work with Ricky? And now, what are you? What's your future?
Yes. Thanks.
Life story.
Well, first, thanks, Hannes, for the invitation. It's great to be able to speak about this recent work so quickly. And then, so I'm I was a PhD student at NYU until May, and then for the last 2 years of my PhD, I was a visiting researcher at Meta. So it was one of these student researchers programs that, where you're allowed to go to Meta and use their resources, and then do research with people there.
Get some GPUs.
Yeah, exactly. Yes, and then so there I worked with Ricky, and I also worked a bit with Brandon, and it was great. So I started. The first work that I was part of there was like this multi-sample flow matching. And then I looked at a bit of stochastic optimal control and how you solve that with deep learning. So we did the first paper where we got good results, but in touch settings. So that didn't got publicized as much as this last one, just because it was not an applicable method for high-dimensional settings. And then, over the past half year, I've been working on this other paper that just came out, where we have this other method, which is Adjoint Matching, that does work. And then we also provide a framework on how to use this method to fine-tune diffusion models. That being said, if there are no more questions, I'll just go over this 6-slide presentation. So I'll spend about a minute per slide. And I feel like this is a way to see the whole content of the paper, and then we can just dive into whichever part interests you the most. There are 2 distinct parts in the paper, if you read it, because you've realized. So I can talk more on the first part or more on the second part.
So more how does adjoint matching work versus more the memory.
Exactly. Yeah.
And then maybe for the Zoom folks, if you I don't know if we can actually hear you. So if you unmute yourself and say something and we don't realize it, then just keep annoying us in the chat also. But then, let's get into
Okay.
stuff.
Okay, so the motivating questions would be, first, what is the best way to perform ILHF on diffusion and flow models? And I realized that this is a question that's more tailored for text to image or text to video or text to audio. But there's a lot of folks here that do bio, and then ILHF is not so the thing that they're looking for. It's more like...
I wouldn't say that's true. Like Jason, for example, he's very interested in fine-tuning.
Right, but they're not so much centered on preferences, rather like other kinds of rewards.
Yeah.
So it's not coming from human feedback. But I think you know what I mean by this question.
Yeah.
And then the second question is, how do we solve stochastic optimal control problems in high dimensions? And that's a bit more general because SOC can be used beyond fine-tuning of models for something from anomalized densities, for molecular dynamics. So it's a setting which goes beyond fine-tuning. And then I think you've seen these images. So we have a base model, and that gives us some generations for a certain prompt, and then we want to get better looking or more consistent generations for the same prompt. So what's the fine-tuning setup? So what are we trying to achieve? We start from a pre-trained diffusion or flow matching model that generates p-base, and then we're given a reward model, R of x, that has been trained using human preferences or whichever other way. And then the goal is to modify the pre-trained diffusion model such that it generates p star that's proportional to p of x times exponential of R of x. So if you're familiar with reward fine tuning for LLMs, the goal there is exactly to do that. So what we did is we're just taking this very natural task and seeing how we can do it for diffusion and flow matching models.
We've seen it all many times in the other papers in the reading group, this type of goal, yeah.
Yeah, and then what does it look like for this particular setting? So we would start from like a base model that generates, so that's a flow matching model that generates this green distribution. And then if you look at this very simple setting, exponential of the reward would have this shape here. So that's the orange curve. And when we, like assuming that we are able to train the fine-tuned model exactly, we would want the fine-tuned model to have these purple trajectories that are able to generate the P-star distribution. And now I'll talk a bit about the stochastic optimal control formulation. This is stochastic optimal control tailored for reward fine-tuning. So you have this first term, which is the control cost, and it measures basically how big the control is. A second term, which is minus the reward. This is because we're doing a minimization problem. And this is subject to the trajectory satisfying this SD. In this SD, we can see the control as a perturbation on the base drift. So for the case of diffusion, the base drift would be just whichever drift we were using to simulate the SD for the base model. And the control U is defined implicitly, right? Because when we have a fine-tuned model, we'll have like the drift for the fine-tuned one. So U will just re-express as the fine-tuned drift minus the base drift over sigma t. And that's how you actually implement or like how you solve this problem for the fine-tuning case. Then one big thing that we studied and we discussed in our paper is that the noise scale that you choose when you fine-tune, when you solve this problem, cannot be whatever. And it cannot be whatever if you seek to obtain this P star that's proportional to P base.
Okay, that's only for like the distribution of paths that you use for fine-tuning or for
exactly.
inference.
For inference, you can still do whatever. So the whole point is if you do the fine-tuning with this particular noise schedule. So it's a bit more subtle than that. So there are some sigmas that don't work. Like you should never fine-tune with those because you'll never, it doesn't make sense. You won't have any connection with the P star that you want. Then if sigma t is large enough, then it has this memoryless property, meaning that the starting point of the trajectory and the end point are independent. But then there's a particular one, and that's what we call the memoryless schedule, such that if you fine-tune with those, you're able to inference either with that same noise schedule or with whatever.
Sure.
So there are, yeah, if you take something that's very large, that has a lot of sigma that's very large, you'll be able to do inference only with that particular sigma. But there's a particular choice of sigma, which is, of course, the one that we claim you should use, that allows you to do inference with that sigma or with whichever sigma you want. And in general, you will want to do that, right? Because the whole point is, like, I think the pipeline for most people will be you fine-tune with the memoryless, the distinguished one, and then you do inference with sigma equals 0, which is what people have been doing anyway.
But like your figure down there already throws up a question. Like on the right, we have the thing that you advocate for, that's the right thing.
Yep.
Then on the left, like on the very left, we have just the pre-trained one. But then the sigma equals 0.2, there's like the wrong thing or the wrong thing to do. And yeah, we all see in this figure it doesn't really end up working. But then we always have these, like, in front of our reward function, if we now just crank it up and have a much higher, or like we crank up the temperature, so crank it down, I don't know, then won't we get the same effect that we get from
it depends on whether you're speaking quantitatively or qualitatively. I agree that qualitatively you'll get something similar, But if you want to get that,
the
right thing, you should use that mesh scale.
But maybe in practice, it then doesn't really end up mattering if we fine-tune our diffusion model.
Yeah, I mean, it depends, right? But I feel like, so this thing that paper that we put is a building block, right? So you want to...
No criticism.
No, I see your point. And this is a very valid point, and this is something that, like, people have been following this philosophy so far for fine-tuning, reward, like diffusion models.
But I mean, I don't want to mess around with my hyperparameter as well. I want to, like, if I know there's something correct, then sure, I want to do the correct thing.
Exactly, so that's my point, yeah. But this is not, like, I'm not criticizing either previous approaches or what you propose, which is, okay, like, let's do some fine-tuning that, like, kind of does what we want, even if it's not, like, theoretically grounded. But if you have something that's theoretically grounded and works, I think, I would advocate for that, because then you can build on top of it, and you know, okay, if everything was well optimized, then this is what I should get. So I kind of understand what's going on.
Yeah. Question. So previous slide. Yeah, okay, for this, like, memoryless. So this doesn't work with, like, an ODE formulation at all?
No. In fact, if you set sigma to be 0 in the problem, the optimum is equal to 0.
This is one thing that we have to talk about later when we're in the paper. Like this, I would want you to explain why it doesn't change with the ODE. But right during inference, we can still run an ODE.
During inference, you can run an ODE.
Your fine-tuned model, you can just use as an ODE. Okay, it's just this training setup.
Yes.
Oh,
but maybe I think it becomes much clearer when we talk about the path distributions and the KL divergences that you write down and so
on. Okay, so and then once we have, like, this has to do with how we set up the problem. So this would be the first part of the paper. And then the second part of the paper is how do we solve the SOC problem. If you look at this problem here, the way people have solved that most of the times is you just parameterize U with a neural network, and then you compute a Monte Carlo approximation of this, and then you know that this value will have dependencies on the parameters of the neural network, so you just use PyTorch or JAX or whatever, and you backpropagate. So it's a very simple algorithm in the sense that it can be written in PyTorch in, like, 2 lines. But the problem with this kind of algorithm is that it's not very stable. So you can use it, but if you try to do fine tuning with this kind of algorithm, so if you set up this problem and you solve it like this, it won't be competitive with the non-SOC based fine tuning methods.
Just because we're, like, back propagating through a inference trajectory.
Yes, it won't, even if you're able to do it, it won't be competitive. But the problem also is that this requires you to store the trajectory in memory, and you can do gradient checkpointing and you can do tricks to alleviate the amount of memory that you need, but you'll need a lot of memory. So there's this memory issue and the stability issue. So what we knew that if we wanted to make this work, we had to basically overcome these issues, and our new algorithm, Adjoint Matching, does both. So what we do here is we first sample trajectories according to this SDE. This is the control SDE. But what we'll do is we'll detach the trajectories. So we won't keep the computational graph. And then for its trajectory, we solve this lean adjoint ODE backwards in time. So this is, we just first evaluate the gradient of the reward, and then we perform this. This is the Euler update. We just use the Euler solver. We didn't want to over optimize that. And to compute this, you just use vector Jacobian products.
Okay, so to summarize, you on the right, on the left, you write down a process to obtain your training target for all the time steps.
Exactly.
And on the left, you write down on the right, like this gradient of the reward function. This guy here is how you get the first gradient.
Exactly.
And then you have the first gradient, and then you get all the other gradients.
Yeah, you unroll. Yeah.
I see. And then you apply all of them to or you put them up here in your training.
Exactly. And this is kind of it's similar to the flow matching approach in that, and for flow matching you want to match to a vector field. The only difference is in this case the vector field that we're matching to is not simulation free.
Yeah.
But I mean, of course, like if you could get something simulation free, that would be amazing. But I feel like it doesn't sound possible. So this is kind of, yeah. I mean, I think it's as close as you can get to the pre-training algorithm, in the sense that you still have a regression problem. And the reason I say memory wise it's better, it's once you have computed the adjoint, so far you have not taken gradients over more than one time step. You need to take gradients of rewards here, and you need to take the gradient of the model here when you do the vector Jacobian product. But you only need to take one at a time. You don't need to store huge computational graphs in memory. And when you're here, when you have access to the lean adjoint state already, you can choose however many you want, points you want to evaluate this.
Yeah, so then how many, like in practice, what do? Do you just take the whole trajectory and run the objective, or do you take like one sample per trajectory?
We were taking about 20, so we were using 40 time steps to simulate both SDs and ODs, and then taking 20 time steps.
Okay.
Also, this is an important point for, like, if you want to implement this, take a look at the last section of the paper where we describe in detail like everything that we used and how we choose where we sample the points. Is not uniform, so we sample the last ones more often.
So more toward
the sample, the clean sample, and this just has to do with image text to image. You want the last ones to be very well learned.
So that's kind of like my question is that, so every time you update the weights, the sample trajectory changes. So you're taking 40 steps and then taking a new trajectory. How do you come up with like that 40 just empirically?
So there was a paper that was the image reward paper, which had their fine-tuning algorithm. They were using 40 steps, so we also used 40.
Okay, so there's a magic number for you.
I mean, I think you would want to use more. We just wanted to run a lot of experiments fast, so we wanted to try a bunch of things, and like the less time steps that you take, the more things you can try in those things.
I have another question. So I feel like this is limited because your reward function is always on x1, right? But if you have like a cost to go function, like reward intermediate time steps, then maybe you wouldn't need to sample your direction.
Yeah, but you would need to estimate that.
Okay, but it's just like how classifier like guidance methods train a
yeah, right. Function. But the thing is here there's no additional model that you need to use, right? You just need to store in memory your flow matching model and the reward model that you're given.
So just why? So you're saying that even if we have the setup where we only have a terminal reward, you would still advocate for training an intermediate reward function?
Yeah, but maybe you wouldn't need to like sample trajectories. You could just do simulation free.
I mean, I think that's possible, and I know that. So okay, I got an email from a group in Denmark, I think, that we're doing this. But I would advocate for this for this reason, which is that you don't have to have another model which may introduce error because you may not be learning it well, and also you have to store it in memory. And also when you do inference, you have to evaluate both your flow matching method and the gradient of the reward, the cluster goal. So it seems like from both training and inference perspectives, it's not better.
But isn't your reward model also like a neural network or something? So you thought about the gradients of it.
But you don't need to have another algorithm, right? Okay, you could argue that once you have the cluster goal trained, you don't need to store the original reward in memory.
Yeah.
So that makes sense.
Okay.
But it's still more complicated because you have more steps to do.
Yeah. I don't know if it's more complicated. It seems like having to resample the trajectory at every 40 steps something could also. There's some hyperparameters with that seem a little bit. heuristic.
Anyway, let's continue later. I wanna get to the meats of why do we need the memoryless fit and
Yes, okay. So this slide has to do with how we evaluated our algorithm, and click score would be like consistency, so prompt alignment. Dream diversity would be diversity per prompt. So we take one prompt and see how diverse the different samples that we get are. And what you see here are Pareto fronts. So in general, if you aim for more consistency, you'll have less diversity. And this is draft one. So this is one of the, I think like it's the best baseline among the non-SOC based. And it was like the best overall before different.
Is this the diffusion model fine-tuning paper where people complain about that so sensitive to the hyperparameters and you have to choose the exact rights, 10 to the minus 6 scaling as the temperature or something like that?
I think there's no temperature here.
Yeah, okay.
Because it's not SOC based.
Ignore my comment and continue.
Okay. And then so this is just we are kind of better predictors. And this is just what the non-SOC methods give you, which is basically overfitting to the reward versus what SOC methods give you. And this is a reward multiplier. So this means like in the exponent you're multiplying the reward by a higher value. So it means that you're deviating more.
Wait a second. So how can you say that the stuff on the right is the state of the art? It produces images.
I know. Well, I mean that has to do with whether you're over optimizing the reward, right? Like if you do early stopping, it doesn't look as bad. Yeah. And like, well, I mean, I'm not. This is not a statement that I'm making up. Like, if you look at the numbers, the numbers for consistency and image quality are the best ones for this.
It's just cool to see that there's actually like some reward overfitting going on.
Yes, but it's normal because if you look at this algorithm, like what they're doing is they're taking the last time step and they're just propagating through the last one.
Okay.
So it doesn't have a lot of memory constraints. It's very fast. But the problem is it's really overfitting to the reward because that's what you're doing.
Okay. Then.
Okay, and that's it.
Okay, nice. Then let's do the. How do I do this? So we are switching to the screen share. Okay, let's start it here. Screen share of the paper. Screen. Start broadcast. Yes. Okay, that's fine. I think that helps. I'm not sure though. And then we can put this guy to the right. And here you go. And then I advocate for here's just basics and setup and so on. Fine-tuning as memoryless, stochastic optimal control, common perspective. And then maybe we can start with you already gave us the problem formulation, right? And then there's this how do we see the SOC as the SKL?
Yes.
That's maybe not so.
I think that's a very good point, especially for like people who do ML and so much.
I would say okay, let's do the initial value. Why is there what would be the naive thing to do, and why is there a problem with it?
I see.
And people on the Zoom, is the paper looking low resolution for you or not? Otherwise, let's go. It's clear. Okay.
I see. Yes.
Kind of low res, but readable.
Okay, so there's one. I'll start from here. So and I think this is a good point.
And if you point, then use your pointer.
Okay, I'll start from here. Which is this connection between, this paragraph is about the connection between SOC and maximum entropy RL. And to see that, I think the key point is to understand that the control cost is just the KL divergence between the measure over trajectory. So this would be the measure over the whole trajectory, conditioned on the fact that the initial state is x0 for the control trajectory. And then this would be the same thing, but for the like this would be the distribution over trajectories, but for the base model.
Okay, so we have the path, a distribution over paths, which is the big fat X, and so big fat X is a path, and then these distributions are now conditioned on a starting point,
Yes.
x0, like a noise point, and we take the KL divergence between these path distributions, and PU is the fine-tuned one, the fine-tuned path distribution.
Yeah. Well, yes. Not necessarily the optimal one. So this holds for n. And if you want to understand how this holds, you can check out the appendix. But the key technique is called the Girsanov.
Yeah, right. The Girsanov theorem. I hear it all the time. What does it say?
So the Girsanov theorem basically tells you that dpu. Oh no, I was writing it the other way. Okay, so. Oh no, sorry.
I think it must be
This one. The base.
So it's like so we're taking the derivative of the fine-tuned process with respect to the base process.
So the first term is a stochastic integral, and note that when you take log, which is what you have to, so when you do KL, you'll have to take log on this, right? So you'll have to take log on this, and you'll have.
I mean, what does it even mean?
Yes.
The derivative with respect to a path distribution.
So you have to think of distributions over trajectories just as distributions over Euclidean space. So what this is saying is that this distribution will be like this one, but you have to important sample all the trajectories. And the important sampling weight will be given by this.
I see.
And why does this term will disappear, right? Because when you take KL is just this.
Yeah, I believe if you do the algebra that.
Yeah.
Okay.
And
good.
And then so the whole point is you have this connection, and that's how you connect.
But the Girsanov says if you have your P base and you have samples from P base, then this exponential thing that you wrote down, these are the weights with which you need to multiply your samples from P base to obtain samples from PU.
Exactly. Yes, that's right. And that also allows you to compute to get this expression for the KL, right? Because when you do this, you get, this is the KL. So the KL between these two things is this. And then when you take log on both sides, you'll have this exponential will cancel out, and this will have expectation 0 because it's just a stochastic integral.
And then in 19 is now the naive thing.
Right. So 19 is when you rewrite things like this, and you get that nice formulation. So how do you go from 19 to 20? This is just a very simple exercise, and for this is a very very general fact for KL regularized problems. So when you regularize this object, like the expectation of something with the KL, you know that the optimal distribution satisfies this this property.
Okay, so you're saying if I now use 19 as my training, like I convert it into some training objective, I do it, then I will end up with sampling 20.
Exactly.
But now what prevents me from just removing all the x0 conditioning on here, and then I'm basically happy in the end?
Well, so that's a very subtle point, and that's in fact why we eventually will need to use Memoryless. You cannot remove the x0 because this equality only holds when you have x0 conditioning here. Otherwise, you don't have it. So Gersonov theorem tells you that this is when the trajectories start from the same point. Because in fact, like if you think of it, what would happen if the trajectories didn't start from the same point? Then you would not know that you can go from one distribution to the other.
Oh yeah.
Because like this is telling you, okay, you have to import and sample, but if you don't start from the same point, how are you going to ever import and sample? Yeah. So these are very good points. And then the whole thing is, okay, but we don't really want this, right? We want to get to P star of X proportional to P base of X times exponential of whatever.
Yeah, okay, but wait a second, here's also something confusing on like, what if we, like, you always have this fixed x0 here now, and of course, if we're training, then, or like if people, when they do their stochastic optimal control thing, then I assume they don't do 19, where they literally always choose x0, but you like vary. Oh yeah, no, sorry, you have written down here that you sample x0.
Exactly. Yes.
Okay, sorry for the discussion.
Yes. So then what remains is how you deal with this, right? And basically, what you end up doing is you end up going from this equation to this equation, and the difference is for this one you have this value function, and this value function appears from this equation going on.
But that's weird. How can it be that the x, like there's a one particular x0 in 22?
Yes, which is the x0 that you have here. So, okay, so the whole thing is, you have that this proportionality thing holds for all x0s, right? But there are some x0s that are more likely than others.
Yeah.
So when you construct an equation like this, that you want to take into account which x0s are more likely than others. So what this tells you is, okay, I want to see how likely its x0 is, and its x0 is as likely as this factor. So you have to include this factor in this equation to account for that.
Mm-hmm.
And yeah, I think I would defer people to read the paper because I don't want to get too much into that.
But I think it's acceptable for me to say it's wrong.
It's the factor that you need to add so that you're able to write equations for the whole trajectory instead of for the trajectory condition on x0.
Yeah.
And I feel like then when we get to this point, when we get to this point, we just have this equation, and then I feel like when you're here, that already asks you to take p base such that p base of x0 and x1 are independent. Because then you'll be able to just integrate out x0, and you'll have just an equation for x1.
Okay, right. So able to integrate out x0, and then we'll. Okay, so now for our fine-tuning objective, because we want to end up with something that gives us a path, like we want to end up with a u that gives us a path distribution that then gives us the tilted one with the right terminal distribution. We want to use still this scheme that you wrote down here, where currently we are also averaging out over x0, but now we want to do it such that the averaging out x0 actually gives you the right terminal reward distribution.
Yes.
Because x0 and x1 are independent.
So and I feel like this is also a point where like going back to this the comment that you made on what happens if you use sigma 0. So this is like the right thing to look at, because what happens when you take sigma 0 is that trajectories are deterministic.
Yeah.
So basically what you'll have is that the value function, remember that the value function is the optimal it's the cost to go. Yeah, value function and cost to go are the same thing. So if trajectories are deterministic, the control is 0. You'll have that this holds. So what you'll be adding with minus, because remember that this is minimization problem, so you have minus here. So this factor will be 1 when you have sigma equals 0. And that means that your problem won't be solving anything. Yeah. Okay, and sorry, I think so we were chatting about.
No, I'm pretty happy now, right? We have our paths, and now you just wrote down everything in terms of path distributions. Sometimes, or like our paths are conditioned on x0, and now we still stay in this framework where everything is always conditioned on an x0. But then in the end, we have our like you write down the joint of x0 and x1. That is like basically a part, like a
exactly. The thing is
our path distribution, right? We only look at this marginal of our path.
Exactly, you're right.
But the marginal that we're interested in the end is the marginal only over x1.
Exactly. So you want to decouple both.
Yeah,
and the decoupling condition is precisely the independence condition between x0 and x1.
Yeah, and like we can compute what is the shit that we're getting by just averaging out x0 in your 23 here.
Yes.
And then we see what we're getting is like some complicated construct and not what you wrote down at the top, not the tilted thing.
Yeah, so if this wasn't like, if you didn't get this, if you were to marginalize out x0, you would have these.
Okay, I'm very happy that this is, or I'm very happy with accepting that this is wrong. No. Then would be fine to move on to 4.2.
Okay.
Any questions from people about 4.2? Yeah.
I have a basic question. So you mentioned that when sigma equals to 0, it seems to be sampled from p-base.
Yes.
Well, like for draft, I think they are also something, they can have some deterministic sampling. But
yes.
Obviously it's not sampling from p-base. What is the gap?
Yeah, that's a very good point.
Sorry, deterministic sampling, is that deterministic fine-tuning or is it deterministic?
Yeah, deterministic fine-tuning, right? Okay. Yeah. So that's a good point, and the thing is that they don't have a connection with SOC. So they're just directly optimizing the reward. One other way to look at it is, if you look at our problem, and this is a detail that like sometimes gets overlooked, but there's a sigma here. So that's another sense. It's not obvious, right? But the fact that when you take sigma equal to 0, like you're basically neglecting the contribution of u. That tells like that kind of, well, it's another way to kind of see that taking sigma to 0 basically makes your u be useless. So you just should not have it, or if you have it, like it won't impact anything. So in other words, like if you have sigma equals 0, you could have u that is different from 0, but then that would just contribute here, and it would not go in your favor to optimize this objective. So you should just take it to be 0, and that means that the optimal trajectory is just like b itself.
So they kind of have that u, but don't have the last one. Like they have the first.
Yeah, exactly. So they don't have this, they don't have this, and they don't have this.
I see.
So that's why they're just simply maximizing the reward, and that's why they get the artifacts.
Okay. Now, this is a very nice explanation just now why this overfitting to the reward happens. Okay.
Okay, should we go into this?
Yeah, like
Yeah.
what is now your solution, your memoryless
Yes.
schedule?
Okay, so I think this is where it gets a bit tricky, but I'll make an effort to explain how we get these two results, which I feel like are the most important
24,
ones.
25.
Well, 24 is what we have already discussed.
Uh-huh.
So 24 is what happens when you have p-values of this form. And it's basically that you can marginalize out x0
sure.
so that you have the marginal for x1 be the right thing.
Memoryless noise schedules.
And then, so proposition one is, okay, like this, at this point we've talked about these memoryless noise schedules, but we have to actually make sure that we can construct them, that they exist and they're available. So
can I have like some intuition here? So we want now P0 to be independent from P1. So now you're trying to just have a, like when you integrate your fine-tuned model, like during integration just adds so much noise that
even the base, so it has to be a property. So this proposition has to do with just purely the base process, because this is a property that we're asking of the base process.
Yeah, okay.
Yeah.
But we're just adding so much noise to the base process.
Exactly.
That x1 will be independent from x0.
Exactly, that's the right intuition.
That sounds like kind of okay, now let's first talk about what you do before.
Yes, so no, I think I was also, so for a long time I didn't understand very well how to make this work. But it turns out that you can pretty explicitly state how much noise that much noise is. And it's this. So that, how do you understand this result? So first of all,
eta?
Right, so eta t comes from your genetic model. So this is, I'm going like to a prior section of the paper, which is this. So this is a formulation for both DDIM and DDPM, where we're writing the vector field as a linear part in the input and the part that's linear in the score. So eta t is this coefficient here that appears in front of the score. So up to this term, it's basically the coefficient that accompanies the score in the expression of the drift. And then if you want to know what it looks like for the particular case of flow matching, that's what it looks like. And if you want to know explicitly for the usual setting that people use, I may be wrong, but I feel like it's this.
So eta is kind of the amount of noise, and the amount of noise already contains the sigma.
Eta is independent of sigma. So that's why the way we defined it was not, we didn't call it the whole thing, but rather we have this sigma and we have eta that just depends on the particular interpolation trajectories that you're using for flow matching. So this is how we call it. There are different notations for this. That's the one we chose so that we didn't intersect with other notations in our paper. But these are the coefficients that you use for interpolation trajectories.
Yeah.
So the flow matching model that you're using when you pre-train informs eta, and it specifies it univocally. So that's what you should use. So that people don't get mad, and I know that this is a bit confusing. Like this blows up at 0, so that's an issue. So what we're using is we're adding h, which is the step size that we're using, so that this problem doesn't happen. And this is like one of the tricks that I explained at last section of the paper. But this is you have to do with this.
Okay, wait. So eta is just the amount of noise that you have during pre-training of your model, or it's like something fixed.
Yes.
And it could be 0, no?
No. Well, I mean, in general, it's not something you'll be able to play with, because the usual setting is you'll have a pre-trained model that has been
No. I mean, or say I don't have a pre-trained model.
I see.
And I now train my model and I do my Yaron-Lippmann flow matching, linear, whatever, and then this eta would be 0, right?
No, because like in general, you'll have that beta t and alpha t are well, in general there will be just t and 1 minus t. Sorry, 1 minus t and t.
Yeah.
So it's pretty. I mean, I'm not saying we didn't look at this. Like we didn't look at if we want to prescribe eta t, can we come up with alpha t and beta t such that holds? But it doesn't look like it's something that people would do. In general, you'll pick alpha t and beta t using whichever properties you want. Maybe you want to use the flow matching schedule. Maybe you want to go to the DDIM schedule, which would be alpha t equals square root of t, beta t equals square root of 1 minus t. But in general, you'll have that. It will given to you. You won't have a say on that, and then that will just tell you which eta t you have to use.
Okay, now you have a formula for the sigma in terms of eta for the memory.
Yes, and then there's also a perturbation here, which was the last edition of the paper. So that was the last thing we realized, which is that you can take this chi to be whatever as long as this holds. So notice that this is not a very strong condition because alpha 0 is also already 0. So as long as this thing is basically finite, you're good to go. It could even be blowing up at 0 as long as it blows up slower than alpha t goes to 0. But basically, you can afford perturbations. And if the perturbations are positive, then I mean this will be even more going to 0. So that's why I was saying, okay, you can take your noise as much as high as you want, and that's kind of intuitive too, because the more noise you add, the more you'll forget. You've already forgotten, but you will just be doing more of the same. But and this is when we go to theorem 1. If within the family of generative model processes, in order to allow the use of arbitrary noise schedules and still generate samples according to the tilted distribution. So that means for any inference noise schedule to work, you have to set chi to 0. So you have to use this particular one. So that's why we call this one the Memoryless noise schedule. Otherwise, what would happen? You could use chi that is whatever, satisfying this, and you'd be able to fine tune, but then you'd be restricted to using that particular chi at inference. And that's not what you want, because in general, and that's the thing, in general, you won't be using a noise schedule that's as high as square root of eta t at inference, because using smaller noise schedules will allow you to have better sample quality at a lower number of time steps.
Yeah, maybe I'm not sure if it's intuition building, but what do images look like if you sample from the base process with a memoryless?
That's a very good point, and I can answer to it.
Okay.
Yeah.
Like, is it very bad? And then maybe also the fine tuning.
So let's look at. So these are some examples, and this is base process. Draft 1, draft 2, we can just look at base process for example.
Yeah,
just for the purpose of
pointy again.
So this would be some images at the base process with it's actually with CFG0. Yeah, it has no guidance. So the thing is, we can also combine, once we have the fine-tuned model, we can use guidance just like whatever. That's how we constructed the Pareto forms.
But here, didn't you write down that it's sigma 0, so it's not?
Yes, so this is the sigma 0, and this is sigma, the memoryless sigma. So you can see it kind of looks, so this is a very, very interesting because it looks different, like definitely looks different.
So I'm also a little bit confused here now. Why do you still get samples that match? Like I would have thought that if this none base here, if this row is really the memoryless one, then they shouldn't match with any of the other rows.
Yeah, and they don't, right? So no, okay, so we're using the same noise seed and the same samples to simulate the SDs for all of them. So that's why they still look reasonably similar.
Okay.
So if you look at this one, so you look at this one, and for example, this one, you can see it kind of looks similar, and this is just because even though they're noisy, they're using the same noise seeds for all of them.
Yeah, it's not just that the noise, like if only the noise seeds, like if only the X0 were the same, then the images
would not, because because precisely they're memoryless, so you'd be adding so much noise, and the noise would be different, units for each particular algorithm, that you would not get the same. But this is also very interesting to see when you're running SOC algorithms, you can see that you preserve a lot more of the original one than when you're directly optimizing the reward, like in this one.
Yeah.
So in this one, even though you're using the same noise seed, the reward is overfit, so you end up having something that looks completely different.
Okay, what else do we need to know about this noise memoryless thing, or are we done there and can go to the adjoint matching?
I feel like, okay, I think it doesn't make sense for us to get into the details, but if you're interested in the more of the mathy side of it, I think, yeah, these two propositions are pretty interesting, and I think they are more like the more math heavy propositions of the
But can you say something intuition building on this memorylessness, as it is sort of that then also our fine-tuning signal becomes kind of weaker because the samples, the samples that we're fine-tuning with, they're kind of worse.
Yes, that's a very good point. And in fact, it is true. Like when you fine-tune and you look at the table. So I'll also talk a bit about this table so you can interpret it. Basically, we have,
maybe for this one we can do zoomies.
Yes, a bit less because so this consistency. So these two are consistency.
Okay, so these evaluate how well we match the reward.
These are no. So we wanted to get metrics that are not correlated with the reward. So the reward that we're using is called image reward. It's a paper from last year that's trained on human preferences. But these other metrics, each of them is computed using a neural network as well. In this case, would be a CLIP model. In this case, it's PIC-score that was taken from the PIC paper. This is human preference score.
Okay.
And then this is taken from this paper.
So they are all just image quality scores.
Yes. So this one is preference score. This is really
except the one
image
that
quality.
Says diversity.
Yes, and this is quality, but it's mostly consistency with the prompt.
Okay.
And so this is the higher the value, the better. And we can see that we do better than the other ones by all quality measures. Diversity is a tricky one because the more diverse model is the base model, but that doesn't tell you much because it just doesn't produce good samples. So it's what you have to look is at the trade-off.
Sure.
Here you're training of basically diversity for image quality.
But what is now the point? Why did you want to bring up this?
Because if you look, this is the memoryless scale at inference, and this is what happens when you do inference at zero noise scale. What happens is, if you look at human preference score, so like the human preference score is higher for this one, but consistency is actually significantly higher for the zero noise scale.
Like if I do the memoryless noise schedule for inference for the base model, then I get pretty shitty samples, right?
Yes.
And
this is for two reasons.
But for after I do your fine-tuning and I do the memoryless schedule at inference time, then the samples are also good.
Yes.
Okay.
I mean, they're so okay. Like all of the good is on the eye of the beholder, right? Like these are some like the most objective way we have of evaluating this.
Yeah, I mean, It's fine. Let's not talk so much about the meaningfulness of results.
Yes.
We want to.
By the way, I want to so this kind of analysis was pioneered by and this was pioneered by another paper from Meta by Pietro and Michal, who is also a co-author here. Pietro Astolfi.
Good. Then adjoint matching.
Yes. Right. So so I think I can do that. I'll cover basically 5.1.1 and then this.
We have now fully accepted that we want to optimize your stochastic optimal control problem with the memoryless schedule. I'm convinced now how you.
Okay. So first I'll talk about the adjoint method, which is what we build on. The adjoint method uses this objective, which is just the control objective, so it's pretty straightforward. 28. And then one way, as I mentioned, is you can just parameterize the control by the neural network. The alternative is you use an adjoint state, which is not the one we use. What we use is the lean adjoint state, which will be a simplification of this. But you use this, you compute this. So the adjoint state is defined such that it satisfies this. So basically, you have this would be the control objective for a particular distribution, and you want to take the gradient of this quantity with respect to the sample at time t. So what you're this object basically answers the question of what happens to the control objective when I modify the trajectory slightly. And then it turns out that, and this was known, although not particularly written for the control setting. This adjoint satisfies an ODE, which is given by 30 and 31. Once you have that, you can compute the gradient of the parameters using 32.
Oh, wait a second. So you're saying there's this this adjoint. It's basically just the adjoint is a function of a certain time and
the trajectory.
And then it gives you the gradients at that time, like back propagated through the
exactly. So if you think of it as, I think the simplest way of looking at it is, assume that you had just instead of continuous times, which is a bit more confusing, you had finite times, and you can move infinitesimally your iterate k, so that how will the remaining part of the control objective, the trajectory that goes after that change?
So here you're basically saying, right? So I can compute the adjoint by I just take my trajectory and then I back propagate through it until time t. But you're saying you can also get the adjoint by you have the gradient at time 1, and then you have the trajectory without the computational graph of it.
Exactly.
And then you can roll out this ODE at 30, 31 to with the initial condition of 31 to kind of back propagate the thing to the next.
Yes, and this is actually so if you
then kind of
this neural ODE
forward and backward differentiation or some shit like that.
This is so if you look at only this second term of 32, this is exactly the neural ODE paper.
Yeah. Whatever.
But the only difference is that we're just using particular the adjoint state here is written for the control problem, but the fact that this is how you can do the fact that you can have this continuous time story, like the differentiate then discretize story is coming from neural ODE. The only thing we're doing here is we're taking neural ODE or like 32. This is not our contribution. Is we take 32 and we adapt it to control.
I think we're all happy with this.
Okay.
Now.
And then
otherwise
yes.
And now
okay, so and this section is just to say that actually there this paper, our paper from late last year, which tries to learn control problems by regressing onto the optimal control. The problem is we had this importance weight, which basically blew up when we had like even moderately interesting problems, so we couldn't use this. But this idea is valid, it's nice, and we exploit it further, just without an importance weight. The way we do it is we can rewrite, once you look at this equation 32, you can just see that the gradient of this is the same gradient as the gradient of this loss here. And the way to see it is if you write this this square and you expand it into the three terms, you get this, which is the first term, this thing, which is the second term, and once you take the gradient of this and the gradient of this are basically
Wait, so this is really again like the core, just like flow matching or diffusion models, that you have like you could match to the let's say the correct thing directly, but you don't do it. You just match to like some conditional quantity, and then because you average over the stuff that you condition on, you end up still with the right.
Yes, I think this is the right way to look at it. But in this case, it's a bit more subtle, right? Because this quantity here, this depends on the current control. So in some sense, you're not matching to the optimal control. Matching to the optimal control is what we were doing here, but that came at the expense of having to introduce an importance.
Ignore this 33. I think that's confusing.
Okay. So, but what I just wanted to say is that if you take this for a control that's not the optimal one, you're not really matching to the right thing.
Yeah.
You're only so you're trying to solve a fixed point problem in the sense that you want to find control U such that when you plug it here and you take this, the conditional expectation of this is actually equal to this is actually equal to the conditional expectation of this.
Yeah.
So this is it's like flow matching, but a bit more complicated in that you're actually solving a fixed point problem. So this is not from the start. This is not what the conditional expectation of this is not what you want to fit, but rather you have to move both U and stopgap U.
So sorry, let me just get rid of some of these so we can see the bars and so on again. So this A here is now literally just so the basic adjoint matching. The A is literally just the adjoint, but now you had a stub grad, and so it's no longer really the adjoint.
No, so it is the adjoint. So this stub grad here is so that we are not backpropagating through the whole computation of the adjoint again.
Okay.
So we want to solve this, right? But we don't want to solve this and then backpropagate through this OD, because like that's not what the algorithm is about.
So, okay, do you know Rob Brakelman?
Yes.
He has a question. He's raising the hand. Can you go ahead?
Hey.
Yeah. Hey. First of all, yeah, awesome paper. Is this so to this point of like estimating? So I think you say somewhere that the expectation of the adjoint is equal to the gradient of the value function.
Right. So
but that expectation is only under the. Yeah, the Costigo.
Yeah.
Oh, but so are you saying that like the expectation should be under the optimal control, but we estimate it under the current control?
Yeah, so if you take the conditional expectation here, this is the gradient of the cost functional at U. Okay. But the thing is, when you plug the optimal control here, this is the gradient of the value function. There's a T here everywhere. So that's the sense in which you're trying to solve a fixed point equation, because in general, what you're taking the gradient of is not what you really want to, but you can't really take the gradient of the value function because you have not found the optimal control yet. So you take the gradient of the next best thing, and then by iterating over and over, you end up converging to the optimal control. And the guarantee that we have is the only critical point of the expected loss function is the optimal control U. So we know if you converge somewhere, you must be converging to the optimal control. You cannot converge anywhere else. Of course, we don't know how fast that will happen. And we don't know, we know that, I mean, it's just, it's tricky, right? It's deep learning. So you don't know what you're actually doing. But if you end up somewhere, it will be the right place.
Yeah, amazing. So yeah, we can calculate A exactly, but the expectation is under the wrong thing.
Yes,
I think
but
it
will eventually
cool.
be
Amazing.
the right thing once we converge.
Yeah. So if we had the right samples, then we would just optimize 34 and we'd be done.
Exactly.
Cool. Thank you.
So
Sure.
like if we had samples from U star, then
you
we
would just
put
use
them in
yeah,
there
exactly.
and be happy. But of course we don't.
Yeah.
Mm-hmm.
So okay. So what do we do? This is basic adjoint matching. So what we're going to do is we're going to modify the adjoint equation to make it simpler. And the whole point with this is too high variance. This gives an algorithm that kind of works, but it's too high variance. So we want to use a different adjoint OD, which is this one, which is what we call the lean adjoint OD.
38, 39.
What's the difference between 38, 39 and the adjoint OD? It's these terms. Well, in expectation, it's this term. So this term here are no longer there. If you look at this, like what we have extra here is this thing and this thing. So these are the kind of things that we will remove.
So let's linger 30 a little bit. We're doing a lot of switching now. So your adjoint now will be the simplified adjoint where you remove the U squared cost.
Yes, and this thing. And why can we do that? We can do it because in expectation and at the optimal control, these terms cancel out.
Let's stay there a little. What do you mean these terms cancel out?
So if you look at those terms above, when you are at the optimal control,
yes,
and you take expectation, you have that this gives 0. So why should you have them even in the first place?
So if you say these terms, you now here are writing down the terms that you marked up above.
Exactly.
That we're
You're right.
getting rid
Sorry.
of.
Yes.
And if we're at the optimal control, then the terms that we're getting rid of, they will be 0.
Yes.
So we can get rid of them, but we aren't at the optimal control, so
True.
we can't get rid
yes,
of them.
But if you look at the proof that we have, or like the statement that we wrote, is that we have the same guarantees that we used to have for basic adjoint matching. We also have them for the new algorithm. So the unique critical point of the expected loss, 37, is the optimal control. So we also have that if we run this algorithm and we do this iterative process and we converge somewhere, we're going to converge to the optimal control. And that's what happens. So I've run this over and over and it's always converged.
Proof by trial.
Yes. So of course, like understanding what the optimization of these algorithms looks like is very complicated. But I think once you know that you converge, if you converge to the right place, and experimentally you converge,
yeah,
it's kind of, well, I mean, it's a pretty safe bet.
Then can we look at your algorithm, and then I think we're happy.
Yes. So what does the algorithm do? And this is an algorithm that's written for flow matching. If you want to check out the DIM, you can find it in the appendix as well. So there are basically 3 steps. The first step, you simulate the OD, and you use the Memoryless noise scale. So that's what you use.
You simulate which ODE of your base model?
Sorry, like yeah, that's a good point. You simulate the fine-tuned model.
Mm-hmm.
So the current like the fine-tuned model with the current parameters that you have.
Right, I see it says here V fine-tune, yeah.
And then, yeah, this is this 1 minus t. So this is what this looks like. And then for its trajectory, you solve the lean adjoint ODE backwards in time. So what that means is you have this, and you start from the gradient of the reward. To compute this, you use the vector Jacobian product. So this is a PyTorch function.
Then in 42, you kind of say that the difference between fine-tune and the original model should be the same as your as this adjoint group.
Yes. So that's a good point. So this thing here, it's not the difference between the vector fields, right? We want to take the difference between the drifts. That's what gives us when you take the difference between the fine-tuned drift minus the base drift and you divide by sigma t, you get the implicitly defined control. So our control is defined implicitly as the difference between the fine-tuned drift minus the base drift over sigma t.
So you're just writing down the u here.
Exactly. So this is, just to be clear, this is u of xt.
Yeah, but I mean in practice we computed it like this. Okay.
And one thing is, if you want to, like, there are some more details that you have to use. Like, for example, we do some loss clipping that you can think of as, you don't want, there are some points in time, especially if you go closer and closer to the noise sample, where this loss can take very high values and then the gradients will be very large. So you want to be careful with that. A bit like the intuition would be as in when you train with PPO, you want to sometimes clip because there are some samples that give you less signal than they do noise.
Yeah.
So you want to get rid of those.
And it's kind of, is it the case that close to noise, we have more noise to get rid of the signal fast?
Yes.
To have our memorylessness?
Right. So there's a reason why when you're close to noise, this is larger. Like first, sigma t is larger because remember sigma t has this expression, so it grows when you're close to 0. But also the adjoint grows when you go close to 0. The reason being that the ODE that you're solving is very similar to like an ODE with exponential solution. So it's kind of exponentially growing when you get close to 0.
Yeah.
And then that's also giving you some, well, I mean, it gives you high values here, so you have high gradients, and maybe you don't want to take all of them. So you just basically set a threshold on this, and that helps you. The other thing you do, and I've already commented on that, is you don't necessarily want to take all the time steps here. Yeah. You want to basically subsample so that they fit in memory, or you subsample a bit, then you compute the gradient, you do gradient accumulation, then you sample some more, and then when you're happy, you just take that gradient and update and discard the trajectories. Okay.
Then anything else you want to mention that's super important?
No, just I think if you want to run this, we're going to probably upload the code later this year or when the paper comes out. This is something that we're discussing. But if you want to run this, I wrote this, which is pretty detailed. I feel like it has everything that you need to know that is not explained earlier.
That's the trick. So
these are the tricks.
The company doesn't allow you to publish your code. You just put the code in your paper.
Well, I mean, these are all the tricks. I promise there's nothing that I left out. Okay. And if you have some issues with implementing this, just write me an email, and I'll be very happy to.
Of course, not share the code, but basically.
No, we're going to share the code, but it's just okay. So the reason we haven't shared the code is the code is a bit dirty. I'm no longer at Meta, so I can't really work on it.
Yeah.
And yeah, I mean that's it. Like there will be someone that will clean the code and release some software engineering grade code.
I also, I there are these companies that prohibit you from doing things easily, and
yeah, but this is not the case here. It's just that yeah, I'm no longer there, so there's some things that I wasn't able to.
Anyway,
to get
more interesting stuff. Any questions? More questions or more?
No, but I want to reemphasize. Just send me an email if you have some issues optimizing this. I've done this with a few people, and yeah, I'm just very happy to help.
Cool, that's nice to hear. Then, I don't know, do I have questions? I wrote down some stuff, but I think over the course, over the course of the discussion, it always came to my mind. But then I think we're done. Any other points? Thank you, Rob, for asking some questions.
Yeah, thanks, Rob.
We have a chat message. Thanks a lot. Yeah, indeed, thanks a lot.
No, thank you. I mean, it's been great to have you anyway.